Good evening, students. Welcome to lecture 4 of topic 2 of unit 3, resistance in circuits. This video will be covering the main ideas of chapter 8.3 of book 1. Please complete this reading before your next class. Here are your learning intentions and success criteria, and a small bug. Please skip that back. Please pause the video and attempt to complete the KS table down below. Don't cheat. Okay, so our learning intention here is we're going to look how resistance behaves in series and parallel circuits and calculate something called equivalent resistance. You see there's only 2 success criteria, they're both about calculations. So in terms of our knowledge, well, we need to know, well, what is this equivalent resistance? And secondly, the skills of, well, how do I calculate those things? And you've got to be able to do it in both series and parallel. Now, in our previous video, we looked at the physical factors behind resistance and we modelled them out within an equation. Now, these 3 things were length, perpendicular or cross-sectional area, and resistivity. I just want to talk about the area a bit for a second. Length is pretty straightforward, it's how long the thing is, but area here is always perpendicular to the length. This is perpendicular to the current flow. If the current is moving through here, it's the area at a right angle to it that is important. And finally, resistivity, which is a property of the actual material itself. But circuits will use multiple resistors in different arrangements, and so you're going to need to know how to calculate how they work together for your final exam. The last bit of assessments we have of the year will be our internal lab and our research investigation, so it won't necessarily be needed there unless you choose to do this as a topic for your student experiment. However, I can pretty much guarantee that QCAA will do a question based off this because it does provide a lot of depth, and so it would be a good opportunity for a high difficulty type question. So let's start with series. When we have resistors in series, that means the current has to go through the first resistor, and then through the second, and so on. So here is a set of resistors in series. We see the current flow needs to go through resistor 1, then it gets to 2, goes through 2, gets to 3, goes through 3. I like to think of resistors as a checkpoint, slowing down the electrons moving through it, like a long queue. Okay? So here we have a queue of electrons, or minors in this case, and they are being slowed down as they have to go through a checkpoint. These resistors in series, think of them as a long linear process that slows everything down. You get to the first point, you wait, you get through, you go to the second, you wait, you get through, the third you wait, you get through, then finally you're done. Now every resistor we add onto it will slow down the current by some small amount. Seems a few little insects you like to play in here. And, well, this leads us to this formula. Okay, so this is the resistance law for any objects in series. Note, the total amount of voltage each resistor will get will depend on the resistance, but the current through each of the resistors are the same, and that will be the topic of our next video when we start modelling with circuits. So for now, just keep it in mind, but this is our resistance law for series. Pretty straightforward. Okay. So let's do an example with this. Here we have one. What is the total resistance of 3 resistors, 10 ohms, 33 ohms, and 100 ohms connected in series? Now, you can probably do this in your head faster than I can write this out. Our formula, resistance total equals resistance 1 plus resistor 2 plus resistor 3 plus whatever number of resistors we have. I believe the formula I used from the previous was just 1 and 2 and then ... But remember, you could do it for 1, 2, 1 doesn't matter, 2, 5, 20, 100. If they're in series, we just add them all together. So let's see, we've got 10 plus 33 plus 100. Oops. That shouldn't be 1,000, that should be 100. And if we think about it in that head, we can see, well, adding them all up together is just going to equal 143 ohms. Don't forget your units. I just want to show something a little bit further than what the textbook does here at this moment, just to show you what we're going to do here. If this was a circuit diagram where we had 3 resistors coming back to a battery of some sort, and we had 10, 33, 100. What we've calculated there is showing that this is equivalent to just having one resistor with 143. They're the same. They would have the same amount of current going through, the same total amount of voltage. Obviously, we can see there's only one loop to have the same voltage on it regardless. But this is what we mean by equivalent resistance. 3 resistors in series with a 10, 33, and 100 is exactly the same thing as just drawing one resistor with 143. Note, this is ideal system where we're pretending that the wires have no resistance. So series is pretty straightforward. Okay? Let's have a look at parallel. When they are in parallel, that means the charge has multiple paths to get through. So if it's coming here from the side, some of the charge can go through R1, some will go through R2, some will go through R3. And I think of it like lanes at a supermarket. If every lane runs at a different speed, then the total amount of shoppers getting through in a period of time will depend on how fast each one works. And the same is true here for current and resistance. As you add more resistors in parallel, the total resistance will always drop. Because just adding one extra bit, no matter how slow it goes, will still get through a little bit more customers than if that aisle wasn't open. Or in case of electrical current, if you had just even one more resistance, even if it had a 20,000 ohmic resistor on it, it would still let through just a tiny amount more charge. Now, the resistance law for these is a little bit trickier, and it looks like this. So the inverse of the resistance total equals the sum of the resistances, or the inverses of the resistors. So inverse of resistor 1 plus inverse of resistor 2, blah blah blah. I would always recommend you work this out in 2 steps. You could rearrange this formula to get RT on top, but you'd have to create a unique formula every single time you have a new thing. There's no easy, well, there is a way to write it so that it works no matter how many resistors you have, but you're not going to like the math. This one works, if as ugly as it looks, it is easier to do this way, so I'd recommend doing it this way. So let's have a look at 2 examples. Here's 8.3b. Here are our 3 resistors from before. 10, 33 and 100 are connected in parallel. Calculate the total resistance of the combination. Note, while I did say that every time we add another resistor on, it means the current gets through a bit easier. It doesn't mean necessarily the resistance gets less, but we'll see what the math gives us. So first what I'm going to do is actually draw this, just so that we can do our equivalents a bit later on as well. So here's our 10, here's our 33, here's our 100, and all these 3 are in parallel with each other. So the current can come up to here, split to go through the 10, the 33 or the 100. Now if we think about this, this has very little resistance, so lots are going to go through here. This has a bit more resistance, so a bit less resistance is going to go through here compared to here. And this has a much higher resistance, so probably if we just look at these 2, this would have 10 times less current flowing through it than this one would. They'd all have the same voltage, so if we draw an EMF source here, they would all have the same voltage going through it, because 1 loop, 2 loops, or 3 loops. So because there's only one thing on the loop, it has to have the same voltage, remember. However, each of them will have different current flowing through it. Now, the formula is that 1 over resistance total equals 1 over R1 plus 1 over R2 plus 1 over R3. That was over 3. So 1 over RT equals 1 over 10 plus 1 over 33 plus 1 over 100. So this is why doing it on your calculator will make it a lot easier than doing this to rearrange. So 1 over 10 plus 1 over 33 plus 1 over 100 is going to give us, so 1 over RT, and I'd recommend writing this as a fraction just because it makes the next step a bit easier. 463 over 3300. And we can see that the bottom here is just the multiplicative of all those, but the one on the top is a very ugly pain in the ass to work out, so let's not do that. And so now we can see that if I want to work out RT will just equal 3300 over 463, which is pretty easy to do. Divided by 463, and so I'm going to give that the approximation is about 7.13 ohms. We can see here that even though we have a 10, a 33 and a 100, this is equivalent to if I had 7.13. Okay, the same amount of battery would be, or same amount of current, sorry, would be running through this system with these, and this is generally what should happen, that you would end up with less resistance, or equivalent less resistance. Okay. And let's have a look at another example here. Calculate the total resistance of a pair of 25 ohmic resistors connected in parallel to a battery whose EMF is 12 volts, and then determine the current. So there's two steps in here. First we've got to calculate the resistance, and that's generally the process all of these questions will have, and then what is the current here. So let's just do those up. I'm going to draw it out first just to help us visualize. Set a pair, so there's going to be two, and we have a battery which is 12 volts. Some people will draw multiple cells there instead of just having the one. However, I just draw one because I'm lazy. That's really all that it is. So let's see, 1 over RT will equal 1 over R1 plus 1 over R2. That equals 1 over 25 plus 1 over 25. Now when you've only got sort of looking for, when they're the same resistance in these sort of parallel things, at least it's easy to add these up. So we can see that 1 over RT will equal 2 over 25. So RT equals 25 over 2 equals 12.5 ohms. Now, our next step is, well, if I redraw this, and this is why we do these things, if I redraw this 12.5 battery at 12 volts, because remember, these are equivalent, these are the same things, they will behave the same. If we slap an ammeter here, and we could have slapped an ammeter here as well, and what is the current that is flowing through that point? That's what it's asking us to work out. Here we've got flow from the battery. Just assume that the ammeter is right next to the battery. So now we can go, well, by Ohm's law, V equals IR, I equals V over R equals 12 over 12.5. So we see that's just under 1, 0.96 amps. We could work out, well, if there is 12 volts, how much current would be going through each of these. So we could have actually worked out, well, how much is going across over one of these, and we can see that would be 12 over 25, which would give us, what's that going to be, 47, 46, 48, 0.48, and then doubled it to get 0.96. So we could have also done that way. So there are multiple ways to solve these things. However, because the question actually asked us to work out the total resistance first, this was the easy way because we had to work that out anyway. Okay, so pretty short video. What we've done so far today, or in this video, is we have looked at the resistance formula for things in series, resistors in series, and we've looked at it for resistors in parallel. For your entrance slip to class, I would like you to look at questions 1 to 4 from chapter 8.3 and copy your answers into the 3.2.4 space on eLearn. Thanks very much for listening, guys. Have a great night.